Okay, Thermo 1 class, I think it's just about time to get started. So we will move on through the slides, and then we will look over some homework problem solutions today. And then we will do all homework problem solutions tomorrow, or not tomorrow, but on Thursday in preparation for the test a week from today. So it will be an hour and 20-minute test. It will be an iLearn. It will be a combination of true, false, multiple choice, and small problems where you have to select the correct answer, hopefully. So with that, let's go ahead and get moving. This slide is where we wound up. This was lectured on at the tail end of the last lecture 6. I think this is lecture 7 for us today. So we will, okay, so we're going to do a little summary here of and introduce the ideal gas model. And so just to recap, the compressibility chart that we're showing over there on the right shows that at some states where the pressure is relatively small in relation to the critical pressure, so that makes the reduced pressure P sub R small, then the compressibility factor Z is approximately 1. And bingo, the circled point up there shows the 0 pressure compressibility factor. And so then the ideal gas law works fine without this Z, without any modification. So if Z is 1, then we don't have to worry about it.
Smoothies are so underrated. They're so good. Smoothies are so good.
I can't. Oh, okay. Guys, please mute yourself unless you have, if you can't hear me or something or have an issue, chime in. Other than that, please mute yourselves. Okay, at such states, it can be assumed with reasonable accuracy. And, you know, what's reasonable and what's not is another question. Author really doesn't go into that. I guess it depends on the accuracy that you need for your particular calculation. Anyway, so at low relative pressures, then it's still okay to use just the standard ideal gas law, which you see down there at the bottom. Pressure, specific volume equals specific gas constant times absolute temperature. So yes, there are a few ways you can screw up this simple relation, and we'll try to cover those. Alternative forms of that previous statement of the ideal gas law. If we want to show total volume instead of specific volume, then P cap V, total volume for the system, equals M, the mass of the system, R, specific gas constant divided by molecular weight. Don't forget that. And of course, T, always absolute temperature in the ideal gas law. This just shows we can work on a molar basis. And remember, if there's a hat on it, you're talking about moles. Okay, throws you back to your chemistry days. So that's the nomenclature in this particular book. So pressure times molar specific volume equals universal gas constant. So that's just the gas constant looked up. It's not divided by molecular weight or anything. It's just the one out of the table times absolute temperature. And then we can also write that previous version on a molar basis. So we have pressure times total volume. N is then the number of moles of gas that we're working with in our closed system. R, again, universal gas constant, and T, absolute temperature. So, you know, you can write this in umpteen different forms, but once you kind of get the gist of it, you shouldn't have any trouble going back and forth, or you should review it to the point that you're comfortable. You can just look at these expressions and know what the difference is between them. Pretty straightforward. Okay, so let's introduce the ideal gas law model and how we're going to use it in problem solving in Thermo 1. Investigation of gas behavior at states where those previous equations, ideal gas law, are applicable indicates that the specific internal energy depends primarily on temperature. Accordingly, at such states, it can be assumed with reasonable accuracy that it depends on temperature alone. So this is a nice assumption that comes with ideal gas. So we'll see our internal energy is only a function of temperature. In reality, it is weakly a function of pressure. And we'll have some curves and stuff like that to indicate such. But over reasonably small pressure ranges, there's not much variation with pressure. And so there's a strong variation with temperature. So we just assume it's only a function of temperature, which simplifies things.
Basically, multiple choice, true or false.
Okay. And as per some of our other definitions, the specific enthalpy also depends on temperature alone. And so you see H, the specific enthalpy, energy per unit mass, is internal energy plus pressure times specific volume. And so if U is a U of T only, a function of temperature, then, and we know that and we're assuming an ideal gas, so for an ideal gas, PV is equal to RT. That's the ideal gas equation. So we can substitute RT for PV. And so we see that H is internal energy as a function of temperature times the specific gas constant times the temperature. So that's a pretty easy derivation. All right. So collecting results, all of those previous equations about the ideal gas model are, plus these two, go together with when we say in Thermo 1 that we're assuming ideal gas behavior, all of those equations apply. And we will see we can have some other simplifying assumptions, such as incompressibility sometimes, that gives us even some simpler ways to evaluate things. So, and we'll be going through that here in the next several slides. Okay, while the ideal gas model does not provide an acceptable approximation in general, so it's kind of interesting. So we spend a lot of time this semester learning how to work ideal gas problems that when you graduate and go out in the world, the solutions of those ideal gas problems is not good enough to use for much of anything. Now, there are a few cases in HVAC, the ideal gas model holds up pretty well, and so those relations get used. So there are some areas, but in general, you get out in the working world, you're probably going to have to do something better than ideal gas law, but this is the simplest starting point at which to introduce thermo. It's the simplest molecular model, like we've talked about, those little molecules being perfect BBs out there floating around in space with elastic collisions off walls when they run into each other. There's no interaction between molecules. There's no intermolecular forces in there. They're just kind of bing, 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 bing. Well, that's nice and simple, but in many, many cases, it's not real world behavior, and it's not good enough to use for design or analysis on, complicated systems that your employer will want you to be working on. So don't get the feeling that this is where it stops when you get out. This is just where it starts when we start trying to train you up on some of this stuff, which, and this is true. And that compressibility factor chart is the illustration of that. When you go and calculate that Z and it comes out to be 0.35, you're going, well, crap, that equation doesn't work pretty well if I got to throw a factor of 0.35 in it in order to get any sort of a halfway reasonable result. So, the first and simplest approach is to go ahead and just look up the compressibility factor or curve fit that or somehow put that into your analysis. But then you'll see that there are much more complicated and better equations of state that you can use and plug those in. Okay. Appropriateness of the ideal gas model can be checked by locating states under consideration on one of the generalized compressibility charts provided by appendix figures A1 through A3. So please do review those figures. They're just better versions of compressibility where they're of a chart like that. The regions are broken down and it's expanded out. And they also have these pseudo-reduced specific volume lines on it as well, whereas this guide doesn't. Just for simplicity, they've left it off. Okay. Internal energy and enthalpy for ideal gases. I mean, I'm sure you've knocked around in the first law enough that internal energy is going to show up in every problem. And when we get to open systems with flow, enthalpy is going to show up in every problem, okay? So being able to, and typically it's an enthalpy change or an internal energy change from some state 1 to state 2 or state 2 to state 3 that we're trying to evaluate. So, you know, making sure that we know how to do that and understand that is pretty important and fundamental stuff that we do in these early chapters. For a gas obeying the ideal gas model, specific internal energy depends only on temperature. We said that. Hits the specific heat, C sub V, as we previously defined, is also a function of temperature alone. Okay? And so that is CV as a function of temperature is equal to du dt, the rate of change of internal energy with respect to temperature. So it's not a partial. We don't have any pressure to worry about. It becomes just a plain, simple, ordinary derivative once you make the ideal gas law assumption, which is nice. Makes integration much more straightforward. Okay, and so upon integration, then obviously we just have multiplied across by dt to put it on the CV side, and then we integrate from temperature T1 to T2, the function CV of T times dt, and that gives us our change in specific internal energy. And if you want the total change in internal energy, well, you just multiply by the mass in the container. So cap U is just little u times the mass. So the units on little u are energy per unit mass, okay? Then that's why it's called specific. All right, so similarly, we have the same behavior in terms of enthalpy. So for a gas, again, obeying ideal gas model, specific enthalpy depends only on temperature. Hence, the specific heat, C sub P, as we have defined, is only a function of temperature. So we get C sub P, specific heat at constant pressure, is how we denote, you know, the verbiage that goes with it. So specific heat at constant pressure as a function of temperature is dH dt for an ideal gas. And upon integration, it's the same deal. The enthalpy difference between state 2 and state 1 is the integral from T1 to T2 of Cp of T as a function of temperature times dt, integrated. So that's all pretty straightforward. Not bad. Okay, these are some slides that I added. This author is kind of notorious. He puts these nice little slide decks out there and then he leaves, you know, a third of the chapter out of them. So, you know, being a good trooper, I have gone back and included those. Because with these electronic lectures, it's difficult for me to write stuff. Normally, I would just scrawl this on the board, and you would have to suffer through my abysmal left-handed handwriting. But in this case, you know, I've typed them out for you, and I'm getting much better in the equation editor, you know. After a couple of days with it, it is pretty slick. If y'all haven't used the equation editors in PowerPoint or Excel or anything like that. You should play around with it. It's really quite good. Okay, so important relationships between ideal gas specific heats can be developed by differentiating that expression for enthalpy as a function of temperature only with respect to temperature. So, I'm not real good at differentiating, but by golly, I think I could get that one right. Right, dH dt is du dt, and R is a constant times T, so that, when you differentiate it, the T disappears and you just get the R, okay? So that's pretty straightforward. So then, from these previous definitions, we know that dH dt, well, that's just Cp of T, and du dt, that's Cv, specific heat at constant volume of T. So we make those substitutions in, and so we get that second equation, Cp of T is equal to Cv of T plus R. So that's an interesting observation. So for an ideal gas, the only difference, the numerical difference between Cp and Cv is the gas constant. Now, it'd be good if you got them all that in the same units. If you start mixing units, you're probably going to get some pretty crazy results. But other than that, there you go. So if you have assuming ideal gas behavior, and you have a Cv and you need a Cp, well, you can try to look it up, or you can just add R to it. And R is easy to find in the tables. So that's of interest to us. And then we can also do that on a molar basis. The only difference between the next to last and last equation is the units change from kilograms or pound mass to kmols or pound moles or whatever. So on the bottom one, we're just doing things on a molar basis. Okay, although both specific heats are a function of temperature, they differ by the constant R, which is the gas constant. So we kind of said that. Let's see now. The specific heats ratio, K, I think we've had that up there before. You'll see that tabulated for different gases. And for an ideal gas, it's only a function of temperature because it's Cp over Cv. When you start working with some of these gases and these equations, after a while, you remember, for air, Cp or K is 1.4 in general. It moves around a little with temperature, but 1.4 is a pretty good number. The other ones I don't work with that much, so I have to look up. And then, just substituting into that previous relation, this definition of K, and doing a little bit of algebra, we can show that Cp is K times R times K minus, divided by K minus 1. Well, see, that's handy to know. That way, I mean, if you know K and you need a Cv or a Cp, you don't have to look up either one of them. Once you find one of them, then you can find the other one. So these are just very handy relations to know that they are out there. And they show up in these problems, that I have assigned you. And so I wanted to make sure that we at least showed you the relations in class. Okay. And I dug these up from the engineering toolbox just to show some variations. Isochoric, that's another word for constant volume. So air, constant volume, heat capacity, which is C sub V. And you can see you've got a numerical value in kilojoules per kilogram per degree K on the vertical or y-axis, and then you got degrees C. And then we have different pressures. So say the low pressures all kind of run together down on the bottom until we get, they start, as we get colder, they start separating some. But for a large range of temperatures, 1 bar, 5 bar, 10 bar, it's all pretty much the same line. So see, that shows the relatively low pressure variation. Then we get at higher pressures, at 10,000 bar, which is quite a bit of pressure, you see you get significant variation in specific heat with pressure. pick a temperature, say pick 200, and then start going up as pressure increases to see how high the pressure's got to get before that CV starts changing a lot on you. So see, that's another way of doing the compressibility factor charts without having to do all those ratios, you know. It's the same information. Then I went ahead and grabbed one for CP, and at really high these really high pressures, CP jumps all over the place. So, you know, you just got to be careful in general. Okay, internal energy and enthalpy of ideal gases. So let's look at some applications where specific heats are modeled as constant. Well, it doesn't get any better than that. You know, you have to evaluate an internal energy change. Well, you can do that integral. If CV is constant, you pull it through the integral sign, and dt integrates into T2 minus T1, the final temperature minus the initial temperature, whatever the subscripts are. So it just doesn't get any better than that. And so the same thing holds true for enthalpy. If CP is constant, pull it through the integral sign, and H2 minus H1 is equal to CP delta T. And of course, that's on a unit mass basis. If you need it for the whole system, multiply it by the mass, the number of kilograms that you have present. For several common gases, evaluation of changes in specific internal energy and enthalpy are tabulated. And here I can show you, I pulled up some of those. If I can do this seamlessly, almost. There we go. So table A22, ideal gas properties of air, pretty nice. And there's one in US units as well. So just be careful. Note we're degrees Kelvin over here. So what is it? 273 is 0 degrees C, something like that, I think. But anyway, so you can look up internal energy and enthalpy right here. These other things we'll deal with more later, but anyway, so you've got nice tables. And these things are accurate. They've been integrated and put together with the variable specific heats and all. So this is, if you can find it in the tables, you're going to get a better answer than if you assume a constant specific heat. You know, and you know, you can work problems, you can go between, you know, 300 and 500, and you can look in the tables and get a specific heat, you can integrate it, and then you can pull the internal energies out of here and subtract and compare and see, you know, how good your simplified answer is compared to pulling it out of the tables. But in general, the tables are going to be better than assuming a constant specific heat because it is changing. So there's air. It goes on down here for a little while. And then, as we would have to go sideways. So then we've got table A23 that has, and now you got to be a little careful. So this is on a molar basis. See the hats on them? So you're probably, so you know, you're going to have to divide this by the molecular weight if you're working in pounds of mass, in kilograms or pound mass. So be careful when you look at these numbers. You see that little hat on there, and see the units up here, kilojoules per k-mole. You can't gloss over this stuff. I'm sorry, your boss won't be happy. Your prototype won't work. The Hubble telescope will be blind, and you will be in a heap of trouble. You know, so do not gloss over your units and look at what's coming out of the tables before you blindly grab the number and plug it in your equation. Okay, so we do have to be careful with this stuff. But anyway, so we get numbers for carbon dioxide, carbon monoxide, water vapor, oxygen, and nitrogen. So far as I know, I think that's about the extent of your gas tables. There may be something else in there. You know, from one addition to the book, sometimes they cram something else in. But at any rate, so these are there for you. Okay. Oh, yeah. And I guess he's going to, oh, yeah, he's going to work a problem for you here. I forgot. Okay. But anyway, so using table A22, that was that first one we looked at, determine the change in specific enthalpy, kilojoules per kilogram, for a process of air from an initial state of 300 K and 1 bar to a final state where T2 is 1500 K and the pressure is 10 bar. Well, first of all, if we're assuming ideal gas behavior for an enthalpy change, do we give a hoot about the pressures? We don't give a hoot. We're throwing away any variation in enthalpy with pressure. So those numbers just don't even come into play. See? Now, if you're plugging into an ideal gas model, you know, PV is equal to MRT, well, yeah, that kind of makes a difference because that's your variable. But if you're just trying to evaluate an enthalpy difference, then, and you're assuming ideal gas behavior, then that's just extra information that's put in there to confuse you. And, you know, professors love to do that. If you want to make a problem hard, give people about 5 more numbers than they need. And they're sitting there going, oh my God, what's that there for? Oh, I don't know what to do with that. Well, yeah, because it's extra information, just meant there to be obnoxious by the instructor, you know? We do that from time to time. Okay, so solution, just what you'd expect. I mean, you know, 300K, look in the enthalpy column, and it's 300.19 kilojoules per kilogram. There you go. And at 1500, we look it up again, and it's 1635.97. See, no consideration of pressure. There's the difference, doing the little subtraction. And so there's a note over such a wide range in temperature interval. This would not be appropriate because there's too much, the using a constant CP would not be appropriate because there's too much variation over that big of a temperature range. So anyway, so there's your solution to this, pretty straightforward. Then there's a little example problem here. A closed rigid tank. So rigid, that tells you there's not going to be any work interaction, right? Because there's nothing that can move. Consists of 1 kilogram of air at 300 K. The air is heated until its temperature becomes 1500 K. So those are the same temperatures, I believe. Neglecting changes in kinetic energy and potential energy for the system as a whole, and modeling air as an ideal gas, determine the heat transfer during the process. So remember, the kinetic energy is 0 because this thing is not sitting on the back of a truck going down the interstate. It's just sitting on the table. We still have kinetic energy of the molecules inside the system, but that's part of the internal energy, and that's not the kinetic energy term that shows up in the first law, energy balance. Now, you're going to get tired of hearing me say that because I'm going to say it every time until the point, if I see somebody actually puke on the table, okay, I might stop. But beyond that, I want to make sure that you realize that because it's easy to forget. You see these, you know, it's all definitions. And the more you hear it, the more likely it is to sink in and become part of you. Same thing for potential energy. The truck is not, there is no truck. It's not, we're not picking the thing up vertically moving. Okay, and so, you know, a diagram is always good. We can do a TV diagram. You can do different diagrams, depends what you know. But we know the mass is constant and the volume is constant, so the specific volume has to be constant. So it's straight up and down. And so on a TV diagram, we show 2 lines of constant pressure for an ideal gas, look like that. And so we're just going from 1 to 2. We're going to heat the thing up and the pressure is going to rise inside the container. Okay, there is our first law for a closed system, a controlled mass. Delta KE plus delta PE plus delta U is equal to the net heat transfer minus the net work interaction. Okay? Well, we have already discussed delta KE and delta PE, and our only relevant work mode here, we don't have any shafts or electric resistors or anything. The volume can't change, so we don't have any way for this thing to do work. There's no work interaction with the surroundings, so the W is 0. So, you know, it's going to boil down to what? Delta U is equal to Q, or Q is equal to delta U. And so, solving for Q, and that's the net. Now, there's not a dot. If there was a dot, it would be a rate. I don't see any dots over those variables, so these are amounts. It's an amount. It's a bushel barrel full of internal energy. It's not a rate of transfer of energy. So you got to get all this stuff clear in your head. Okay, so Q is going to be the mass in the container, just times the specific internal energy at 2 minus the specific internal energy at 1. And bingo, what are we going to do? Well, shoot, we got a table for air. We're going to go look those puppies up and plug the numbers in. So there we go, looking them up. It's the same column, but now we're in internal energy instead of enthalpy. So the enthalpy is the U plus the PV, the pressure times specific volume. The U is just internal energy by itself. So I guess that's at 300, so that's U1, 214.07. U2, it goes up to 1205.41. 1 kilogram was the mass. But just, you know, put it in your calculator and you get 991.34 kilojoules is the heat transfer. Now, that came out positive. What is our definition of positive heat transfer? Heat added to the container is positive. Are we adding heat to the container? Yes, we are. So all that jives, and we should be pretty happy with that answer. Okay, there you go. All right, let's go on to polytropic processes. That's our old P. It can be specific volume or it can be total volume. In this case, it's total volume raised to a constant exponent n, and all of that mass on the left is equal to a constant for the process line, whatever the process is. As you vary the exponent, it could be all kinds of different processes. The exponent n may take on any value from minus infinity to plus infinity, depending on the particular process. So for any gas or liquid, okay, you can use the polytropic process concept for liquids as well as gases. When n is equal to 0, the process is constant pressure. Well, that's pretty clear because any V to the 0 power is 1, and 1 times P is equal to a constant, so that says P is equal to a constant. Okay. So if you're given that and it says assume for one case or whatever n is equal to 0, then that's just a constant pressure process. If n is equal to plus or minus infinity, then it's a constant volume process. So if you look along like a PV diagram, then that line is just a vertical line, and in the positive direction it just goes forever, and in the negative it goes forever. So anyway, that's numerically that means it's a isometric or isochoric process. And then when n is equal to 1, it's a constant temperature process. So, you know, if that's PV, well, if that's an ideal gas, if it's an ideal gas molecule for an ideal gas when n is equal to 1, yeah. So PV would be equal to RT. Well, guess what? R and T is just a function of temperature. So, and it's a constant. So if RT is a constant, then temperature has to be a constant. So anyway, you can rationalize these things out if you think about them a little bit. But anyway, so that's what those different exponent values, what types of processes they refer to. Again, you can put specific volume in there instead of total volume. For a polytropic process between two states, you can write it like this. You know, if you're going from a 1 to a 2 to a 3, well, P1 V1 to the n would have to be equal to P2 V2 to the n, because at any state, PV to the n is constant. So you can relate that as many times as you need to. That can be a kind of a trick in problem solving to realize that. So if you know P1 V1 and you know n, then you know what the constant is, and then you can set that constant equal to that same equation. Say you didn't know V2. Well, if you know the constant and you know P2, then you can, and the n, then you can solve for V2 or likewise. Or you can rearrange it, just do a little algebra on it, and you can show it that way. And these are in your book, but this is stuff I added that I just felt like we needed to, you know, put it up and make sure that everybody had seen it and thought about it a little bit. Okay, so for a polytropic process, where n is unequal to 1, you know, we're often interested in evaluating the PDV, the work, you know, compression work, expansion work, you know, a change of volume work. And so if you have that polytropic process, n is not 1. You see, this equation kind of has a problem when n is equal to 1, right? You get a division by 0. And so it kind of blows up on you. So you got to do something else. You got to go back and do the integral again when n is equal to 1. But anyway, there's a relation that you can use. When n does equal to 1, we go back and this thing integrates into P1 V1, or that could be P2 V2, you know, since they're going to be constant times the natural log of the final volume over the initial volume. So these last 4 equations apply to any gas or liquid undergoing a polytropic process. When the additional assumption of ideal gas behavior is appropriate, additional relations can be derived. So this chapter 3, you need to get your book and just, you know, when you study this stuff, just kind of page through and look at these relations, because we got a whole slew. So, you know, and some apply for this assumption. Some, you know, we make an additional assumption, we get some more, we make an additional assumption, and you just have to, you know, I mean, I can sit up here and harangue all day long, but until you just sit down and work a few problems and get that set in your mind, it's just going to swim around, you know. But we'll look and see what else we can do with the additional assumption of ideal gas behavior. Okay, so polytropic process for an ideal gas. So we can, and these are not too hard to derive, but anyway, I didn't go through the derivation, but you can see the relationship T2 over T1 is equal to P2 over P1 raised to the power n minus 1 over n. And that T2 over T1 is also equal to V1 over V2 raised to the n minus 1. And so you can see in working problems, depending on what you're given, you can juggle these things left, right, and sideways, okay? For a polytropic process with an ideal gas where n is unequal to 1, then we can get this relation. So MR, that's, you know, ideal gas, you know, PV is equal to MR kind of a thing. Or what, PV is equal to MRT, so whatever, anyway. For polytropic process, when n equals 1, that's constant temperature, I believe, we get this. So I think the combination of just reading through these things, make sure you understand when each one applies, working the homework problems, and studying the example problems in the book should get you pretty comfortable with using these different relations. And I think this is the last slide. For an ideal gas, case n equals 1, just a reminder that's a isothermal process. Okay, so that's pretty good. What time we got here? So we're 9:30, 10:30. So we've got a while to look at some problems. So let's do that. I called up. These are some that I looked at that I thought were pretty good. There are a few, I think they're mostly out of the second assignment, which you don't have solutions on yet. So I don't think you've seen these solutions. I'll be sending those out tomorrow to you. So, yeah, let's see, I've got the problem statement. So this first one is problem 60. Okay, there we go. That gets it all on the screen. So we've got a tank, and it's got some ice water in it. Okay, so shown in picture 360 there, we got a tank. It's open to atmosphere. And initially, where we start this process, we've got 2 pounds of liquid water at 180 degrees, I'm sorry, at 80 degrees Fahrenheit. And we've got 4/10 of a pound of ice at 32, okay? All the ice is gonna melt as the tank contents attain equilibrium. We're gonna assume no significant heat transfer occurs between the tank contents and the surroundings. So that's out the top or the sides. And we want to determine the final equilibrium temperature in degrees Fahrenheit. For water, the specific enthalpy change for a phase change from solid to liquid, i.e. melting, it takes 144 BTUs a pound. You know, that's a real good number to memorize. If you take a pound of ice and you want to melt it, you got to put 144 BTUs of energy into it. Likewise, if you have a pound of water at saturation and you want to freeze it, you got to suck 144 BTUs out of it in order to solidify it. That's kind of interesting. Now, I'll give you a little side note here. When I teach the HVAC class, we always talk about tons of cooling. You know, if you've ever looked at window air conditioners, you know, a 1-ton window air conditioner is a good sized window air conditioner. If you go check your heating and cooling unit at your apartment, it's probably 2, 3, 4 tons, depending on how big your apartment is. Your parents' house is probably 3, 4, 5, 6 tons, depending on how big their house is, okay? Well, where does this ton unit come from? That's kind of a strange unit, okay? That's actually a rate of heat transfer. So back in the day, when my grandmother was a kid, they used to keep stuff cold in an ice box. And I don't know if you've ever seen an ice box. When I was growing up, we had one in my basement. We didn't, thank heavens, we didn't have to use it, but it was down there. It was just an antique. And it was a big, thick wall cabinet that had 2 doors on it. And down at the bottom door, it had a big tray down there. And so the ice truck would run, and you get a block of ice, and you put it down there, and you set it in that tray, and you close it up, and it would slowly melt. And then, you know, the water would go down in the tray. You put your food up above, and that melting ice, you know, every pound of ice that melted, it would suck 144 BTUs of energy, you know, out of the air in that space, and it would keep it keep it cold so your food didn't spoil. Well, the ice truck ran every once a day, you know. Now, I don't know what happened on Saturday and Sunday. Maybe you had to double up. I don't know. I wasn't around back then. But anyway, so the idea here of this ton was, okay, the ice truck is going to run every day, okay? And so let's take, let's say that we bought 1 ton of ice, which is what, 2,000 pounds, and it's going to be 144 BTUs of refrigeration per pound. So 2,000 times 144 equals 288,000, and the ice truck runs every 24 hours, divided by 24. That's 12,000 BTUs an hour. And that's the definition of a ton of cooling or a ton of refrigeration. It's the removal of 12,000 BTUs an hour. So that's where, it's interesting where some of these units might come from. I don't know all of them, but I happen to know that one. So I thought I'd share that. Okay, enough of this. Let's go back to the problem here. Okay, so we got 2 pounds of water, 80 degrees Fahrenheit, 4/10 of a pound of water at 32, mixed together. We're going to dump them together, no other heat transfer, and we're going to see what the final temperature of this water is going to be when it all melts and all that good stuff. Okay, so we don't need to read the first little bit. There's the picture. Engineering model is probably good. Closed system is the liquid and the ice. For the system, heat transfer with the surroundings can be ignored. Kinetic potential energy play no role. The thing's not moving anyplace. Liquid water originally present and the ice melt are modeled as incompressible with constant specific heats. We'll make this as easy as possible. Pressure remains constant throughout 1 atmosphere. Specific enthalpy change, and then there's the 144. So we've already been through that. Okay, so let's write. What do? We write the first law. So there you go. Delta U, delta KE plus delta PE is equal to Q, but we say we don't have any Q, equals minus W. Okay, and the only work is constant pressure. So the P will pull through the integral. It's just P times delta V. And there is a small change in volume, right? Because that ice is going to, what? Let me see. It expands on ice. Water expands on freezing, right? So that ice will occupy, when it melts to water, will occupy a little bit less volume. And then when we cool down that water, it'll shrink a little bit. Not very much, but there is, from the start to the end of this, there is a slight change in volume for the system, okay? So we've got delta U, and so this is going to be, I've got a minus PdV over here, so I just bring it to the other side, so they're all on the same side. Well, but I look at that, and delta U plus P delta V, well, that's delta H, by golly. That's a change in enthalpy. Kind of FYI, that's the definition of it, okay? So we can work this as delta H equals 0. So that's what the first law is going to tell us. So in evaluating that equation, we recognize that the ice initially present melts, and the ice melt, the water formed, is raised in temperature as the temperature of the liquid initially present decreases, right? Okay. So eventually all liquid achieves the final equilibrium temperature, T sub F. And so let's start breaking this equation 1 down into its various component parts. So now this looks like a minus sign, but it's not. It's part of this bracket. When I first looked at this, I said, man, that looks like a minus sign. And then I looked over on this side and I said, ah, that's just the way he's drawing the brackets. So that's not a minus sign. Because I was going, I don't know why that would be a minus sign. Anyway, so delta H for the ice to liquid transition at 32. And then that same liquid will increase from 32 to whatever the final temperature is, which is what we're trying to solve for. Okay. And I will email this sheet, all these solutions out to you. So you will have this. And then plus, then you've got the original water, the 2 pounds of water that was at 80, and it's going to wind up at T sub F. It's going to cool down a little bit because energy is going to have to come out of it in order to melt the ice. And then it all comes to equilibrium together. Okay? Well, if you're working in US units with water, and it's incompressible. So C, it's no longer CP and CV once you say incompressible, it's just C. So that is correct. And C is 1 BTUs per pound per degree Rankine. Well, that's pretty nice, 1. But, it doesn't screw up the numbers if you leave it out, but it does screw up the units. Okay, for water, and you can look that up in the table. Okay, so just plugging in numbers, we've got 4/10 of a pound, and it's going to increase in enthalpy by 144 BTUs a pound, so whatever 4/10 of that is. Plus that 4/10 of a pound is going to increase to TF from 492, and that's Rankine. Is that an R? That looks like an F to me. If that's an F, he gets a demerit. He gets a point off on his solution if that's an F, right? Because 492 is not F. That's Rankine. Okay. Okay. And so, but I think the signs are correct because this is going to increase as it melts in energy. This is going to increase in energy because then it's going to warm up from here to here. So this delta T will be positive, plus 2 pounds of water, specific heat of water. And so this one is going to wind up cooler than it started. So this is going to be negative, but it's going to cool down. And so that's appropriate. Okay, so you got to make sure that you write these delta T's in the right order or you'll get the wrong answer. Your balance won't be right. Okay, so look at that. And beyond that, you just have to solve this equation, one unknown. You get, assuming his math is correct, you get 508 Rankine, which is 48 degrees Fahrenheit. Okay? All right, very good. Let's look at 79 here. And so we have 2 kilograms of oxygen fills the cylinder of a piston cylinder assembly. So we're going to have, when you see piston cylinder assembly, you're probably going to have constant pressure work. Unless somebody puts a spring on top of it, so that force is going to change. But generally speaking, a piston cylinder device establishes a volume change at constant pressure. That should be your suspicion when you read a problem that says piston cylinder, you go, I suspect constant pressure, expansion or contraction. But you got to read the whole problem. The initial volume and pressure are 2 meters cubed and 1 bar respectively. Heat transfer to the oxygen occurs at constant pressure until the volume is doubled. So we're going to double the volume. So we're going to heat this thing up. Say it's sitting on the table here. We got a Bunsen burner under it. We're going to put heat in there, and that's going to expand the volume. And we're going to do it so that this piston cylinder is frictionless. And so that piston comes up and it maintains the same pressure the whole time as that thing comes up and down. He's showing it on the side, but it doesn't, I mean, it doesn't matter conceptually. Okay, determine the heat transfer for the process in kilojoules, assuming the specific heat ratio is constant at 1.35. So this is oxygen, air is 1.4, so in general, kinetic potential and energy effects are ignored. So again, it's not on the truck and it's not going up and down and that stuff. Okay, so there's our picture. Engineering model, closed system, controlled mass, pressure's constant, oxygen, model is ideal gas, specific heat ratio is constant, and we're throwing away kinetic potential energy. So there you go. There's our good old first law in all its glory. So we throw out delta KE, delta PE. We get delta U is, so the total change in internal energy for the gas is equal to the net heat added minus the net work performed by the system on the surroundings. So delta cap U is the mass times delta small u, which is U2 minus U1. And since K is constant, CV is also constant. Okay, so that's a good point to note. When you hear constant K, that means, that implies constant CV and constant CP because they're both involved in K. So, you know, yeah, I mean, this is a lot of the trick of thermo is knowing the code words. You know, when I hear adiabatic, it means no heat transfer. Well, if you don't know what adiabatic means, then you're pretty well screwed, you know. So when you hear constant K, that means constant CV. You know, it's like a word association kind of a game. Okay, so then our delta cap U is the mass, and that's integrating what? You pull the CV through the integral sign, you can see it, and it integrates into T2 minus T1, so we can evaluate that. So for the delta U, we want to use this. And then for work, well, work, this is pretty nice, pretty sweet for work. It's constant pressure work, PDV, so that's P times the V2 minus V1. You know that. That's the integral of PDV. Pull the P through. And so when we collect all of that, we can say that, that we're just solving this for Q, so the W comes to the other side. And so we get Q is delta U plus PDV plus the work. Okay. Well, now we got to go find some numbers. Okay. So now we're going to use the ideal gas law because we're making ideal gas assumptions. We don't know the initial temperature, but we know pressure and volume. And if you know any two and you assume ideal gas law, you can solve for the third. Okay. So that's what he's doing here. So T1 is equal to, and you don't have to put P1 because P is constant. You can put P1, but P1 is P2, so it doesn't matter. So pressure times volume at 1 divided by the mass, and this is the specific gas constant, right? That's universal divided by molecular weight. Okay. Plugging numbers in, 1 bar, 2 meters cubed, 2 kilograms. Here's his gas constant, 8.314. Divided by 32 is what he's taking the molecular weight of oxygen to be. And once you do the division, the units are kilojoules per kilogram per degree K. Now for me, probably the hardest part of this is making sure I get these silly units right. Because look at this. I got bar here. So 1 bar is 100,000 newtons per meter squared. And then I've got kilojoules, so then I got to divide, that's a joule, so then I got to divide by 1,000 to get to kilojoules. So, I mean, I can't do any more than just point these units out. You're going to have to study them on your own and get used to juggling the units. But I would say, you know, 50 to 75% of the mistakes on a test would be unit mistakes. I mean, and it sucks. I mean, until you get used to them. It's just, there's some things in life you never like. I never liked spending time on units. I just wanted to understand the equations, but you can't get the right answers without getting the right units. You know, it's just something you just have to learn to put up with. Okay, anyway, that comes out about 385, 384.9 Kelvin. And remember, you get a temperature out of this, it's coming out in absolute. It isn't coming out in degrees C. Absolute temperatures, absolute pressures. Okay. Well, so we know P1 is equal to P2. Well, this is an expression for P1, and this is an expression for P2 from the ideal gas law. You know, PV is equal to MRT. Well, so this is P1 is equal to MRT divided by V1, but P1 and P2 are the same, so that has to be equal to MRT2 divided by V2. The mass are the same, the gas constants are the same, so you can use this relation to solve for T2. And it turns out that yeah, the ratio of volumes, we know V2 is twice V1. That's where the T's blanked out for a minute. So that means the temperature is going to be twice at state 2. So it winds up 2 times this is 769.8. So now we got T1, we got T2. We can evaluate CV. So this is our R, universal divided by M, divided by K minus 1. So that's that little relation that we had. So there's the gas constant divided by the molecular weight, and then that divided by 1.35, the K minus 1, and we get the CV is 0.742. So that's what we're going to use to evaluate the internal energy change. So that CV times delta T times the mass is the total internal energy change. All right, so there we go. Sticking it all in together, 2 kilograms times the specific heat times the temperature difference plus the work term. So this is the pressure. This is the change in volume from, it goes, it ends up at 4 minus 2, and the unit conversions. And we get 771.2 kilojoules. That's a pretty good problem. Not any one piece of it are very hard, but that integrates in quite a few of these concepts. You know, that's a good problem. That's a good problem. Okay, we got time for one more. This is coming out right on time. Let me see. Get out of there. Don't do that. Thank you. There we go. All right. So this is 393. Air contained in a piston cylinder assembly undergoes 2 processes in series. So it does one and then the other, as shown in the figure below, we'll look at. Assuming ideal gas behavior for the air, determine the work and heat transfer for the overall process, each in kilojoules per kilogram. So it's asking for those in specific units. And I will say, you know, on a test or anything, if it says assume ideal gas behavior, you do not have to check for Z. Okay. Now in the book, I can't guarantee for him, but this is just homework, you know. So, but on my test, if I want you to check for Z, I will make it pretty darn clear that we are concerned. So I say something about we are concerned about real gas behavior. Well, the only way you've got to check real gas behavior is to check Z. I mean, that's your only tool. You know, you're a one-trick pony when it comes to checking for real gas behavior. Check your Z. Okay. Okay, known, find, stuff. So there's our processes. So we got P, and this is total volume. So we're constant pressure to here, and then we have an isothermal process to here. Okay. So let's take a look. Well, and let me see what we're asked to. We want to find the work in the heat transfer. So obviously we're going to have to find the work. Well, this first one's pretty easy, right? That's PdV like we just kind of did before. So just plugging that in, and you're given the volumes on the chart. So there's not much to that. So there's your pressure, there's your volume change and all that. With the conversion factors, that comes out 40 kilojoules. Now, is that positive work or is that negative work? What's our definition of positive work? If it's done by the gas on the surroundings, it's positive. Well, so if that piston is moving out, then we're doing work on the surroundings by the gas. If that piston is moving in, the surroundings are doing work on the gas. Okay, so this is appropriately positive. Let's see. So using the ideal gas equation of state, we're just going to solve for mass. So P1 V1 divided by RT1 will be M. Again, just plugging in the values. So we've got 0.2323 kilograms is the mass. And this is air. Note the molecular weight of air, 28.97. Before we had oxygen and it was 32. So you have to tailor that universal gas constant for whatever gas that you have in that cylinder. Okay, so we have to know the mass because this 40 kilojoules is cat W, right? That's for the whole shebang. And so, but we want specific values. So we want kilojoules per kilogram. So I have to divide that out. And I get 172.2 kilojoules per kilogram. Okay. Now, we're starting over here at 300, but we don't know the temperature here. We do know this is isothermal. So if I can find T2, then I know the temperature for this whole process. Okay. And so since T2 is constant and pressure is equal to just the ideal gas law, PV is equal to MRT. So he'll find this temperature in a minute. But this is the expression for work from 2 to 3. So this is pressure as a function of volume. So you substitute it in. MRT is constant. And so we get the integral from V2 to V3 of dV over V. And we know that integrates into V3, the natural log of V3 over V2 times MRT2, which could be T1 because it's the same temperature. Okay. Process 1 to 2 is at constant pressure. So we're going to write the ideal gas law for both of those pressures. And we also know that we have the same mass, so we can cancel out the mass. And so this is where he's solving for T2. So because that pressure is the same, I know RT1 over V1 is equal to P1 is equal to P2 is equal to RT2 over V2. The R's go out, and so then the temperatures are just the volume ratio times the initial, and I wind up with 900 K. So all of this process occurs at 900 K because it's isothermal. So here I'm evaluating that work. So RT2 ln, just plugging in the numbers. And he's already divided by the mass here. Yeah, let's see. Yeah. Yeah, because if you divide through by the M, then this will come out in kilojoules per kilogram. So once you plug the numbers, we get 179 kilojoules per kilogram. And so then the total work is the sum of these two numbers are 351.2 kilojoules per kilogram. So that's the work number that we're looking for, okay? Then we're going to go back to the energy balance to calculate the heat transfer. So this will be capital Q, the total net for the whole system is the total change in internal energy plus the net work. And so then the delta U is the mass times U3 minus U1. And plus the W. And so let's see, he's pulling data from A22. That's the table. We can check that. I didn't do that. But so we're at 300 and we're at 900. So this should be the internal energy at 900 minus the internal energy at 300. So let's think. Don't get dizzy. Okay. And this is air. So let's see. Well, here's 900, 674.58, where that number came from right there. And we got the 300 number. I think we looked up the 300 number before, 214.07. Okay. Oh, gosh darn that thing. I did it again. Ah. There we go. 674.58, 214.07. And that's already in kilojoules per kilogram. So we're good to go there. There's the net work. Add them on, you get the net heat transfer. 811.7. And he's got a little note down here. How are we doing time-wise? We're fine. Note that the heat transfers Q12 and Q23 could be determined from respective energy balances. So, I mean, you could do it for each process and add it together, or you can do it for the overall process, which is what he did. So if you do it for process 1 to 2, you just have to look up U2 minus U1, and the whole internal energy change comes there because this is a constant temperature process. And so this contributes nothing to it. So if you add all that up, it balances. Okay? Well, I think that's pretty good. We're a few minutes short. But I'll email out those problem solutions and be working on those. I mean, the whole key is going to be definitions, understanding what the terms mean, and being able to apply some of these simple equations. And find states, look up stuff, saturated, superheat, compressed liquid, all that stuff using the tables. All right, thank you. Have a great day.